You're watching a Channel 98 NBISD TV production.
And then I says to the guy, "Hi, Parabola." What? Oh. Hey, welcome to Deja Vu. It's Algebra 2. I'm your host, Kevin Corpy. Hey, did you ever wonder what the headlights in your car and getting a drink of water from the water fountain have in common? No, you probably haven't thought about that. But believe it or not, they do have something in common. And the thing that they have in common is that they both involve parabolas. Yeah, parabolas. Now, parabolas are the true last of the conic section. And I know I told you on the previous 3 episodes that we weren't going to talk about them because we talked about them previously on previous shows in the context of a function. But then I got a lot of phone calls and emails from some very angry parabolas saying that they want their due attention in the spotlight of a conic section episode. So, by popular demand, today we're going to be talking about parabolas in the context of a conic section, which doesn't necessarily mean it's going to be a function. So if you want to know how headlamps and drinking water from a water fountain have in common and how they're related to parabolas, then you're not going to want to miss today's show. Download the worksheets from the district website and stick around with me for about 30 minutes or so and learn a thing or two. Let's get started. All right, lesson 31, parabolas, continued, okay, in the sense of a conic section. So what is a parabola and how does it relate to a conic section? Well, you know a parabola is just the curve that looks like the U. It opens up or down. That's the function parabola. That's the quadratic function. But parabolas can be curves that are not considered functions. They'd fail the vertical line test. And they actually are obtained from slicing a cone. Let me show you how we're going to slice the cone. Here is a picture of a cone. If we slice the cone at an angle that is parallel to the cone itself, to the side of the cone, that slice will come out the bottom and the cross section will end up being a parabola. Okay? Now remember, if we slice it parallel to the base, it's a circle. Perpendicular to the base is a hyperbola. If we slice it at any angle coming out the other side, then we get an ellipse. But when we slice it at an angle that is specifically parallel to the cone and we come out the bottom, the cross section is a parabola. Here's another picture of what it looks like with the exploded view, with the breakaway view. So this little shape right here is a parabola. Now parabolas basically come from the Greek prefix para, which means parallel to, and bola, which means to throw. And so if we just throw this plane through that cone, parallel to the side, the cross section will be a parabola. Okay? So it's to throw something parallel to. And so the word parallel itself actually is the same Greek root, para, which means parallel. Okay? So what do we use parabolas for? Well, parabolas are probably, in fact, the most useful of all the conic sections, and they're the most commonplace, except for maybe the circle. Now, if you've ever thrown something up into the air, or you've jumped, like in a long jump, the trajectory that your flight path will follow, or the ball's path will follow, traces out a parabola. Parabolas also have very nice reflective properties, which I'll talk again on the end of the show. And the reflective properties are very useful whenever you're trying to concentrate something to a single point. Okay? So here's a little preview of what we're going to be talking about. So that's what a parabola is. Let's get to the locus definition. All right, the locus definition of a parabola. Here it is. It's the set of all points in a plane, a flat surface, whose distances from a fixed point, which we still call a focus, to a fixed line, which is called a directrix, are always equal. They're always the same. The distance from the fixed point to the parabola and from the parabola to that line called a directrix are always the same. Here's a little diagram of what I'm talking about. We've got the focus. This is still called the vertex, just like it was in a hyperbola and an ellipse. It's the vertex. And here's the focus. It's inside the curve. If I drew a line from the focus to any point xy on the parabola, and then I draw a perpendicular straight down to that same distance, if I let this distance hang straight down, that will touch a line that runs perpendicular to the axis of symmetry, and that line is called the directrix. So for simplicity's sake, if I let my vertex be at the point 0, 0. I'm going to call the focal length now P. And the reason I'm not calling it C is because typically for all the other conics, we had something called a center. A parabola doesn't have a true center. Its most important point is the vertex. And so in this case, the distance from the vertex to the focus, we're going to call P. Well, that precisely by definition is the same as the distance from that vertex, which is on the parabola, to the directrix. And so P units up to the focus, P units down to a point that's on the line that is the directrix. Okay? Now the point that's directly, consequently, between the focus and the directrix is the vertex. Okay? So let's go ahead and look at the anatomy, essentially, of the parabola and look at the equation in standard form. It's a little bit different than we looked at previously. For parabolas that were functions, they had to open vertically. They had to open up if the leading coefficient was positive, or negative, or down if the leading coefficient was negative. Parabolas don't have to open vertically. You're going to see in a second here that they can open side to side. Well, for the ones that open vertically, they still are functions, so we're going to be able to solve them for y. But we don't want to do that. We want a different form. This is going to be the standard conic form of a parabola, which will give us the information we want directly from the equation, namely the vertex and P, the distance from the vertex to the focus. So here's the standard equation. It's y minus k equals 1 over 4p times x minus h squared. If you were to expand this out and collect your constant k on the right-hand side, you would have ax squared plus bx plus c form. But that's not the most useful form. If we write it in this form, we have our vertex now at hk, and our p, notice, is part of the coefficient of the squared term. And when it opens vertically, our x is still squared, just like it was for a function. This line here would be the directrix. This line here, x equals h, is the axis of symmetry. That's the one you can fold the parabola on, and that was true for all functions. Okay? But if a parabola opens horizontally, it's no longer a quadratic function. However, it's still a parabola. And that would look something like this. Here's a parabola that opens sideways. Okay? If it opens sideways, that's not a function. It fails the vertical line test. But it does have an equation, and we're going to kind of model the same behavior. Except in this case, if it opens sideways, it's the y term that's squared, and we're essentially solving for x, the non-squared term. So that's going to be x minus h equals 1 over 4p, y minus k squared. So h is always with the x, k is always with the y, therefore the vertex is always at hk. P is still the distance from your vertex to your focus. We're just going to be moving horizontally. Now, whether a parabola opens up or down depended on the leading coefficient. Okay? Same thing here. If it opens left or right versus up or down depends on the sign of the leading coefficient, which in essence is going to be determined by the value of p. So you can actually think of p as the directed distance from the vertex to the focus, which means if p is positive, it's going to open up. We're going to move in the positive direction, which is up, to the focus. Or if it happens to open horizontally, if p is positive, it's going to open to the right. We have to move in the positive direction, which is to the right, to get to the focus. So if p is positive, it opens up or to the right. If p is negative, though, it's going to open down. That's going to reflect down, or it's going to open to the left. Okay? So that's not shown here. It'll open the other way. So there you go. Positive p, positive direction. Negative p, negative direction. Got it? All right, I think we're ready to try one out here. All right, so here we go. We're going to try one ourselves. We're going to graph the following parabola. And when you graph it, we want to show the vertex, we want to find the focus and show the focus, and we want to sketch in the directrix and maybe even write its equation. Yeah. Now, what you want to do is first analyze it. And notice that it is a parabola. How do we know that it's a parabola? Well, because there's only one squared in it. All the other conics, circles, ellipses, hyperbolas, had x squareds and y squareds. Parabola has only one squared term. If it's the y that's squared, that's not the way you're used to seeing it as a function, which is the up-down variety. So when the y is squared, that's going to be the horizontal variety. Okay, so what we need to do is try and get it into standard form. It's solved explicitly for x. That's not what we want. There's this plus 2 lingering over there on the right-hand side. We want to bring it across. So by subtracting 2, we get x minus 2 equals 1/2 y plus 1 squared. That is the standard form. Now I can identify my h, my k, and my p. This is my h. That's related to my k. and my p is related to the coefficient of the squared term, but it's not explicitly found. So the vertex, let's go ahead and list that right here. The vertex v is at 2, because it's x minus 2. And since this is y plus 1, that's really y minus, the standard form, negative 1. So the vertex is at 2, negative 1. And now I want to find p. It's the directed distance from the vertex to the focus. Well, remember that the coefficient is really 1 over 4c in either of the two forms. So what you can do then is you could take the coefficient 1/2, set it equal to 1 over 4c, and then you have a little proportion that you can solve. So if you do that, you get 4c equals 2, divide both sides by 4, and you get c equals 2/4 or 1/2. And it's positive. Because it's positive, and I called it c, didn't I? That's a bad habit. It's p. Remember, c was the focal length for all the other conics. So, easy mistake to make. P is 1/2. And because it's positive, it's moving in the positive direction from the vertex, which in this case is to the right. So, let's go ahead and sketch it first. Here's my coordinate plane. You want to plot the vertex first. 1, 2 to the right, down 1. There's our vertex. Our directed distance to the focus is 1/2 units in the positive direction. Since I know, again, that the y is squared, that's going to open horizontally. So I have to move 1/2 unit, which is going to be right there at 2.5. Now, if you think of the parabola as being a mouth, and it's hungry for the focus, it always eats the focus, okay? And so the way you'd sketch that then is you'd carefully draw it going this way and carefully draw it going that way, all right? So the vertex is essentially at the point 2, negative 1, and the focus right here is at the point 2.5, negative 1. It's a 1/2 unit to the right. Now, where would the directrix be? Well, the axis of symmetry is horizontal. You can fold that parabola horizontally and it'll coincide. So the directrix is perpendicular to that. It's going to be vertical line. And it's going to be a 1/2 unit behind, in this case, of the vertex, which is going to be right there at 1.5. And if I just draw a vertical line going through the point 1.5, I'll go ahead and label it x equals 1.5. Okay? And there's a nice little sketch of the parabola, showing the vertex, labeling the focus, and the directrix. Now, here's one thing to consider. How did I know to draw the parabola with this width or this aperture? Why didn't I draw it wider, or why didn't I draw it narrower? That's a good question. You can either find the x-intercept here and see where it crosses as a guide to how wide, and then by symmetry it opens the same on the bottom. But unlike an ellipse and a circle, or even a hyperbola that had the slant asymptotes, there's no way to tell directly from the equation how wide this thing is. There is another important piece of information that you could find called the latus rectum that will basically be a chord that is parallel to the directrix, that basically the bigger it is, the wider, and the smaller it is, the narrower. And that would essentially pass through the focus and go to the other side. And so the length of that kind of determines the aperture. If your teacher wants you to do that, that's fine. Otherwise, a nice little general sketch is probably sufficient, depending on what you want to do with it. Okay, there you go. All right, let's take a real quick break from parabolas. I need one. You probably need one. While you're gone, think about this. Why was the small little ant, why was he so confused? The answer when we get back.
It was not. It was like...
It's easy to tell if you've had way too many. But what if you've had just one too many? Buzz driving is drunk driving.
When you give up the ability to decide for yourself, you give up what makes you, you.
Welcome back to Deja Vu with Algebra 2. I'm your host, Kevin Corpy, talking to you today about parabolas in the context of a conic section by popular demand. Now, what did the little baby ant, why was he so confused? He was so confused simply because all of his uncles were ants. A bad joke is a cue to get back to something I do much better than joke telling, math. Let's do it. Okay, so we had the equation, we sketched the graph. Another thing that you should be able to do is to write the equation from either the graph or from pieces of information that allow you to generate the graph and then subsequently the equation. So what we want to do here is we have a picture of a parabola and we want to write its equation. Okay, simple enough. Notice this dotted line here is the directrix. The directrix is shown and we have a nice coordinate plane that we can count. Basically, we need to figure out first of all if it's going to be vertically or horizontally, and then we need to find the vertex and the distance from the vertex to the focus. Okay? Or we can actually find the distance from the vertex to the directrix, because remember, those are the same for a parabola. We just have to be careful about the sign. So this one definitely opens vertically. It opens down. So this is the function. That means x is going to be squared. All right? So here's my standard equation based on that. It's y minus h equals 1 over 4p times x minus k squared. That's the equation that we're going to have to use. Do we know where the vertex is? Well, let's see. Notice our scale here is counting by 2s. 2, 4, 6, 8, and 2, 4, 6, 8 down. So it looks like our vertex is at 2, 2, 4, 6 down. So our vertex is at 2, negative 6. Okay? That already gives me the h and k. All I need to do is find p. Well, my focus is not shown here. So for a parabola, remember that the focus and the directrix are the same distance from the vertex. Okay? So if here's my vertex, and it looks like my directrix is right there, this point would end up being the point 2, and then down 2 plus another half of 2, negative 3. So that point is 2, negative 3, and my vertex was at 2, negative 6. So they're on the same vertical line. How far is it from negative 3 to negative 6? If you had to walk, you'd count 3 paces. Okay? So the distance is 3. Now, is it positive or negative, my p-value? Well, it's the directed distance from the vertex. So if I wanted to sketch the focus, I'd have to go down 2 plus another 1, which would be there. And I had to go down to get there, so that would be negative. Or you could say it's opening down, so it's negative. So p is really negative 3. And that's the number one thing that most students kind of overlook, the sign of p, because you have to interpret that yourself. Opening down or to the left, it's negative. Opening up or to the right, it's positive. Now we just drop this into the equation. Here we go. Y minus negative 6 is y plus 6 equals 1 over 4 times p, which is negative 3, times x minus k, which is 2. And now what we'll do is we'll simplify that. Just in the coefficient, y plus 6 equals negative 1/12. Oops, I forgot my squared, but I haven't walked away from the problem yet, so that's good. You want to look things over one last time before you walk away, and everything looks pretty good at that point. So this equation is this graph right here. If you were to solve for y by subtracting 6, you could put it in your calculator, and you'd get something that looks very similar to this. Of course, you would not be able to see the directrix, nor would you be able to see the focus. But writing an equation in this manner allows us to get the information we need to quickly sketch it. So it's preferred in conics rather than expanding it all out. Got it? All right, let's try it again, but this time no graph. Okay, we're kind of doing it by instrumentation only. We want to write the equation of the parabola in standard form, whose focus is at 4, negative 5, and the directrix is at x equals 12. Well, the first thing I want to do is see what it is I'm doing. So I'm going to graph this and plot the information. The focus is at 4, negative 5. 1, 2, 3, 4, 1, 2, 3, 4, 5. That's right there. I'm going to put a little f by it so that I remember it's the focus. Okay, it's not the vertex. It is a point, though. And the directrix is at 12. Ooh, that's way out here. X equals 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That is a vertical line. X equals is a vertical line. Y equals is horizontal. Based upon those two things right there, you actually know if it opens vertically or horizontally, and you also know if it opens left, right, or up or down. You know it, right? Okay? Remember that the parabola has to eat the focus, right? And the vertex is halfway between the focus and the directrix. So my vertex must be where? Well, if this is going to be at x equals 4 right there, this is at, let me get a pen that writes, there we go, that's at x equals 4, and this is at x equals 12, how far is it in between there? It's 8 units. So half of that is 4. So if I go another 4 units to 8, 4, 1, 2, 3, 4, there's 8, and another 4 to the directrix would be 12, or you can just add them and divide by 2 to get the average. That's the x-coordinate of the vertex. Now the vertex and the focus are on the same axis of symmetry, so they're going to have the same y value. So right there, I know that my vertex is at the point 8, comma, and then since the focus was down 5, so is the vertex. Now you know, since the vertex eats, or the parabola eats the focus, we can draw it like that, we can draw it like that, and there's a nice little sketch of it. But do I really even need that? Well, probably not, but it's fun to draw. I have my vertex, all I need is P. It's the directed distance from the vertex. Here's my vertex, I have to go left to get to the focus. Left is a negative direction, and I have to go 4 to the left. So P is negative 4. It's negative because it opens to the left, or it's negative because I had to go left from my vertex to my focus. Now we drop it in. Let's pull out the equation first and then drop it in. It's going to be of the form x minus h equals 1 over 4p times y minus k squared. Because it opens horizontally, it's the y that's squared. Now we just drop in our hk and our p. So here we go. It's x minus 8 equals 1 over 4 times p, which is negative 4, times y minus negative 5, which makes it plus, squared. And you typically want to go ahead and simplify the coefficient. 4 times negative 4 is negative 1/16. So my final answer, x minus 8, is negative 1/16. I'll pull the negative out front, times y plus 5 squared. And that looks pretty good. I've got all my squareds in. Vertex is at 8, negative 5. Yep, got it. Piece of cake. But it was only a piece of cake because I sketched it first, I oriented myself, and I actually counted the distances to get my vertex and my P. Okay? Drawing a picture really helps. Try it. You'll like it. Now it's time for Deja Review. All right, we'll kind of keep the trend going on Deja Review of looking at the reflective properties of the conics. And the parabola is no exception. It is a beautiful conic because of its reflective properties. Okay? Now, the path that a water takes as you're sipping out of the fountain does make a parabolic arch. It does. Okay? And that's just pretty. A jumper that's in a long jump will make a parabolic arch. Again, that's pretty. But the parabola is really useful in its reflective properties. Okay? The trajectory is useful for physics if you're trying to map out a path. But in this case, let's focus in on on the parabola and how the focus is related to the reflective properties. Okay, in your headlights, you have a single lamp, and it emits light in all directions. But behind that lamp, you have a reflective surface that's curved. It is curved. Did you notice it was curved? Well, it's not any old type of curve. Guess what type of curve it actually is? It's a parabolic curve. A three-dimensional parabolic curve. And here's a diagram of what it would look like. The interesting thing about a parabola is that anything that enters parallel to each other will reflect off the surface of the parabola and go to the focus. And in reverse, anything that's emitted from the focus will bounce off the parabola and leave in parallel beams. And that is exactly why a headlamp, a simple headlamp with a parabolic mirror behind it, works so effectively. A single lamp by itself would flood the area, and it wouldn't really let you see further down the road. But by reflecting it off into parallel beams, you actually get a really concentrated focused beam that can brighten up an area in a specific location with higher intensity. Okay? Parabolic. That's when we're emitting from the focus. Well, it works in reverse. If you have signals coming in, they can bounce off the focus and actually be concentrated at a single point. And that's how the satellite dishes that may be hanging on the side of your house work, or one like this. You have signals coming in, and you have a parabolic arch back here, and the signals that come in will bounce off the parabola and they are concentrated to a single point here, which is the receiver. And the concentration of the signal is what allows you to hear things or see the picture on your television set. By itself, if you're just out there trying to catch these individual signals, you get a very weak or fuzzy signal. But concentrated to a single point gives you the crisp, clean clarity that you appreciate when you're watching TV, right? As long as it's not stormy or cloudy outside. So those are the interesting reflective properties of a parabola. Now here's a specific example. If you've been to a sporting event, you might see the guys on the side and they're holding up these two-handled things, this big clear dish, and a little microphone sticking out. What are they doing? Well, they might be eavesdropping on the other team's plays, although that's illegal, right? We don't want to relive Spygate, but it could happen. Those things are very, very cool machines that have real-life math designed right into them. They are called parabolic, yes, parabolic microphones. Okay? Here's what one kind of looks like, an artist's rendition. All right, there it is. Kind of looks like a bullhorn. But basically, you hold the handle, you have a microphone boom out here that's sticking out into space, you have the curved dish behind it. And it works very much like a satellite dish. And this piece right here goes into your ear or it goes into a recorder and it captures the sound. And it enables somebody to hear something very, very far away with maybe a faint signal. It's concentrated at a single point. Okay? So let's say that you're constructing your own homemade parabolic microphone. It can be done. The surface of the parabolic microphone is going to reflect the sound to the focus, which is precisely where our microphone is placed, precisely at the focus. Well, we need a physical object to extend from the base of the parabola to hold the microphone. And that is called a feed horn. Okay? It sticks through the parabola and it extends the microphone out, the feed horn. Well, if we happen to know what the equation is of the cross-section of one of these parabolas, which when you're ordering these things to make your homemade one, you can buy them with different type of apertures, and that's important to know. So let's say that we know the equation of the cross-section is x equals 1 over 32y squared. That means our parabolic microphone's opening sideways, right, to the right. How long should we make the feed horn, right? If the focus is such a critical point for reflecting the sound to, you have to make the feed horn length exactly, correctly, precisely the right length, or it's not going to work. Okay? Well, remember, all we're looking for is simply the distance from the vertex, which is right there, to the focus, all right, which is our value of p. Notice that this is the coefficient of the squared term, so 1 over 32 must equal 1 over 4p. And we're dealing in inches here. So if we cross multiply there, we get 4p equals 32, and if I simply divide by 4, I get p equals 32 divided by 4, which is 8, and that's inches. So as you're making your homemade parabolic microphone, and if this was the equation of the cross-section, you want that feed horn to extend exactly 8 inches out into space, into the dish of the parabolic microphone. Place your microphone receiver at the tip, one, that will transmit the sound into a recording device or into your ear, and you can eavesdrop on people, okay, or record sporting events. Either one, all right? Cool stuff involving math. We are out of time on today's show of Deja Vu with Algebra 2. I've got everything in, so I think with the previous episodes and today, you know quite a bit about parabolas, and that's a good thing, okay? Now, this was the last week for Conic Sections. There are some applications that we're not going to get into. So next week is going to touch off the beginning of the end of the show. We're going to talk about some interesting things that you might encounter in your Algebra 2 class at high school as we near the end of the year. So I hope you'll join me as always. But until then, I'm Kevin Corporate reminding you to continue to do your homework.